What we just saw on this first warm-up exercise was a limit that gave us the indeterminate form after direct substitution of 0 over 0. Now, let me just kind of remind you here that whenever you are evaluating these limits, especially on the free response section of the AP exam, be careful with your equal signs. You don't want to say that this limit here is equal to 0 over 0, which is undefined here. You don't want to say it's equal to an undefined. It should be equal to a number, or it is undefined if it, you remember those three ways that it's undefined, or does not exist due to unbounded behavior, which we could use with either a plus or minus infinity. You could have differing left-right behavior, or you can have that oscillation. Okay, so we'll talk a little bit more about what the AP exam would expect in terms of notation as far as whenever you go to evaluate these limits on the free response section. Is it going to show up? Probably. Anyway, so when you have this indeterminate form, what we had to do is we had to factor that thing. It's not the only thing that you could do. You could try to, it depends on what you have. Maybe it was rationalizing the denominator or the numerator. Maybe there was a common denominator that you had to get rid of because you had complex fractions. There were all kinds of different tricks. So after we factored this one, cancel out a common factor, there was our -4 as our answer. Okay, so let's look at this next one. It's another rational, a rational function that we're taking the limit of, but this one as x approaches infinity. So as x approaches infinity, we're talking about in behavior here. In behavior, it could go either to positive or negative infinity, right? So it's sort of like either this kind of thing, or, well, this one's actually this vertical asymptote that's right there, but or it could be a horizontal asymptote, right? So that's what the limit is here to help us to determine. All right, so what do? I do a direct substitution, just like I always do first. All right, so if I mentally directly substitute in here, I'm going to have big O infinity squared times 3 minus 1, still infinity on the top. And on the bottom here, infinity squared times 2 plus 1. Yeah, still infinity. Infinity over infinity is another indeterminate form. Probably going to have ourselves some sort of horizontal asymptote, and we have to see what it is. Okay, so what's the trick whenever we are, when we're taking a limit and we have infinity over infinity? Well, what we do is we divide by the highest power of x. It's in the denominator here, which is the x squared. So I'm going to rewrite this as 3x squared minus 1 over x squared divided by 2x squared plus 1 over x squared. And now just simplify. Got a limit. This would be a 3 minus 1 over x squared over 2 plus 1 over x squared. And now I'm ready to evaluate the limit by sort of like a direct substitution, pretending like infinity is this really big number. So it doesn't affect the 3, doesn't affect the 2, but it does affect these little terms. I have 1 divided by some sort of infinity squared. Any number divided by a number that's getting infinitely large, that's going to 0, right? Remember that. These things are going to go to 0, both of them. No. This one, yes. That and that, both of those things are going to go to 0, and we're left, as we can see, with the limit of 3 over 2. Horizontal asymptote. And of course, we had a pre-cal rule which said that, hey, whenever the ratio, whenever the exponents are exactly the same here, you just take the ratio of the leading coefficients, which was 3/2. And it's associated with the fact that these things are growing relatively at the same rate, just so this one is at 3 times that rate, and this one is at 2 times that rate, since these are both squared here. It has something to do with L'Hopital's rule when you think in terms of those things. All right, let's look at one more of these. Third warm-up question. Another limit. What do you know? Take the limit as x approaches 0 of e to the 2x minus 1, and this minus 1 is not in the exponent there, over 0. What do we do first? Direct substitution. E to the 2 times 0 is going to be 0 minus 1 over a big fat 0. Well, we know it's already undefined. Oh, watch your equal sign there. And then e to the 0 is 1. 1 minus 1 is 0 over 0. It's indeterminate. So chances are what we have here is what you kids are calling a POD, a point of discontinuity. It's a removable discontinuity. We just have to fix it. We have to uh, fill in that little hole. It's that googly eye that fell off of your project, right? And you're searching for it, you're searching for it, you need to glue it back on. Where are we going to glue it? Okay, so with the 0 over 0, we had things like what we can try is factoring. Let's try to factor this thing. It looks factorable. Looks like the difference of two squares that's right here, right? So let's try that. So the limit as x goes to 0, this would be e to the x plus 1 times e to the x minus 1. All right, fantastic. Over x. And then what I want to do is cancel out some common factors here, which I don't have any, which means it didn't help at all. This was completely unhelpful, which I'm going to get this crayon out and cancel that whole thing out. Okay, so that didn't help. Let's see, what else do we have? We have like rationalizing, like with a conjugate. Well, that I don't think that well, here, there is a conjugate that's associated with this. Let's just give that a try, I guess. Multiply this by, let's see, e to the 2x minus 1 over x. Let's multiply it by a fancy 1, e to the 2x plus 1. Let's see if this gets us anywhere. Okay, and so I would have the limit again, and on top, maybe I leave it in factored form. Maybe I expand it out, whatever. So if I expand this out, it's e to the 4x minus 1 over x to the, now I'm not going to expand this one out, 2x plus 1. Okay, so whenever I stick in 0 again for this, 0 up top, this is e to the 4 times 0. This is e to the 0, which is 1. 1 minus 1 is 0 on top, and on the bottom, it's 0 times, I don't even care, it's still 0. That didn't help either. Oh, you know what? I've got another idea. We could divide the top and the bottom by the highest power of x that's in the denominator. Let's just try that one. Limit as x goes to 0, e to the 2x minus 1. We're going to divide that by x over x divided by x. Okay, let's see if this helped. Okay, on top, nothing cancels out. That's okay. But on the bottom, I get x divided by x, which is 1. So I have the limit as x goes to 0 of e to the 2x minus 1 over x. Wow, look at that. It was very, very unhelpful. And you know what? To be honest with you, this last one is only supposed to work whenever we're talking about infinities, not when we're talking about 0. Anyway, I just thought it'd be fun to do, and look how much fun it actually was. Yeah, so none of the tricks that we know work with this one. So there's got to be a different approach. And there's this French guy that's got our back for this one. So, well, you remember back in the day, whenever we were first learning to evaluate limits, what we did is we looked at a graph or we looked at, a table of values. That's what we're going to do next. But here's a recap of what we did with that infinity over infinity business right there. Okay, so here it is. It's in factored form, which was totally unhelpful. Yeah. So let's look at the graph of this particular thing and look at some table of values, throw some numbers down in here. Hey, well, look at this. If I look on either side of the number of 0, it looks like it's approaching the number 2. Remember, whenever you take a limit as x approaches 0, we're looking to see what the graph is approaching from both sides of the number 0, and it looks like it's the number 2. Let's confirm that with a graph, shall we? Well, here's a graph, and if I zoom in on this graph right there, it looks like it's hitting the number 2. Now remember, there should be like a little removable discontinuity, little googly eye that fell off your project. That's right there, and it does give us some indication that it should be too. Okay, all right, well, of course, when I'm having to do this, or whenever you're having to do this, on the AP exam, you probably won't have a graphing calculator available, not on some of these questions. So we have to be able to do it by hand. So let's take a look at another way. Since we're right around 0, one of the things that we could do is we could approximate each one of these things with its local linear approximation. It's tangent line, basically, right? Okay, so that's what we're going to do now. So here's the bottom. Well, obviously, it's just y equals x. You don't have to do any kind of linear approximation for that one. But here is the top function. This is not the local linear approximation. It's the actual function that's right there. But let's approximate it with its actual tangent line. That's right there. Okay, so we have a slope of 2 here, and we have a slope of 1. And remember that what we had before on that last example is that I'm going to dial it back here, is that it looked like that the limit was approaching the number 2. And if I look at both of these slopes, 2 divided by 1, I also get 2. Well, here, let me explain. Let me come back over here. And let's just look at the tangent lines for each one of these. So the first one, writing with a laser, of course, we've got e is equal to e to the 2x minus 1. If I'm going to find a tangent line, I need 2 pieces of information. I need a point. It's going to be e of, or y of 0 is equal to e to the 2 times 0 minus 1. That's e to the 0, which is 1 minus 1 is 0. So I have the coordinate 0, 0. Right? And then I also need a slope, so I need to take its derivative. That'd be 2e to the 2x, because I have to use the chain rule on it, and now plug in 0 again, and 2e to the 2 times 0, e to the 2 times 0 is just 1, times 2 gives us 2, there's our slope. And then we're going to write our tangent line thusly. Okay, there's my J-Leno bracket. And I've got y minus 0 is equal to my slope, 2 times x minus 0, which, we could just write as y is equal to 2x. So far, so good. Now, I don't have to approximate the bottom as a linear function because it already is. So here's the deal. We're going to take the limit as x approaches 0 of e to the 2x, all of this minus 1 over x. This should be approximately equal to the limit as x approaches 0. I don't know what accent that was, honestly. It should have been French. It's approximately equal to 2x over x. Why is that? Because we're talking about really super close to 0, and this function can be approximated by y is equal to 2x, super close to 0, and then I don't have to approximate this one. And now I can see with my cancellation crayon, these 2x's cancel out, and then I just get 2. All right, so what we just did is that we basically had to find some slope here, right? We had to find slope. Hey, what's the slope of this bottom here? It's 1, right? And that is associated with derivatives, and all of that is associated with L'Hopital's rule.